What if everything we know about how galaxies form is wrong? For decades, astronomers believed the early universe should have been filled with tiny, chaotic galaxies. Small collections of gas slowly growing over billions of years. That is exactly what our best cosmological model predicted. Then, the James Webb Space Telescope looked deeper into the universe than ever before and found something that should not exist. Instead of seeing cosmic babies, Webb found massive galaxies packed with billions of stars. Fully developed only a few 100 million years after the Big Bang, some were so unexpectedly bright and massive that astronomers nicknamed them impossible galaxies. The researcher even said he almost spit out his coffee when the numbers appeared on his screen. At first, many thought it had to be a mistake, but as more observations came in, the mystery only grew. By 2026, Webb and the Euclid mission had uncovered ancient quasars, mature spiral galaxies, and even giant galaxies that had already stopped forming stars far earlier than our theories said was possible. So what did the James Webb really discover? Did it break our understanding of the universe, or reveal that the cosmos has been hiding a much stranger story since the very beginning? To feel why those galaxies shocked anyone, you need the expectation they violated. Modern cosmology's workhorse is called Lambda CDM, a universe built on Einstein's general relativity, cold dark matter that clumps under gravity, and dark energy that drives late-time acceleration. That model does not only describe today's sky, it also predicts a timeline for how structure should grow after the Big Bang. The predicted timeline is hierarchical. After the hot early universe cooled enough for neutral gas to form, mostly hydrogen and helium-filled space, dark matter, which does not shine, pulled that gas into shallow wells. First, mini-halos. Inside the densest pockets, the first stars ignited. Those first stars are often called Population 3 in the jargon. Massive, short-lived, metal-free, their light, deaths, and leftovers seeded heavier elements and helped carve bubbles in the fog of neutral hydrogen during cosmic reionization. Small galaxies should have come next. Irregular, chaotic, low in total stellar mass. Over billions of years, gravity would merge those dwarfs into larger systems. Spirals, bars, quiet disks, and giant ellipticals would be late products. Architecture that needs time to cool gas, settle rotation, and survive repeated collisions. Milky Way-class stash of stars packed into an organized galaxy a few 100 million years after the Big Bang was not the textbook opening act. It was supposed to be the middle or the end of a long construction project. That expectation was not a wild guess pulled from nowhere. It came from N-body simulations of dark matter, hydrodynamic simulations of gas, and decades of observations that seemed to match the slow-build story wherever telescopes could see clearly. The Hubble Space Telescope became the public face of that story. For more than 30 years, Hubble's deep fields pushed the frontier of visible and ultraviolet light, catching galaxies when the universe was hundreds of millions of years old, often quoted in the ballpark of 400 to 800 million years after the Big Bang for some of its deepest reaches. But Hubble had a hard ceiling. Light from the earliest galaxies is stretched by cosmic expansion, wavelengths that left us ultraviolet or optical cruel toward the infrared by the time they reach us. Astronomers call that stretch redshift. At high enough redshift, the light Hubble was built to catch has slid out of its best windows. Hubble's mirror is about 2.4 meters across, powerful, and still partly blind to the cosmic dawn's most redshifted light. The James Webb Space Telescope was designed to open that window. Its primary mirror spans about 6.5 meters, coated in gold to reflect infrared efficiently. It sits about 1.5 million kilometers from Earth, near the second Sun-Earth Lagrange point, away from our planet's heat, so its instruments can stay cold enough to see faint infrared glow. The mission pitch was straightforward: find the first luminous objects, watch galaxies assemble, and test whether hierarchical formation looked like the simulation said it should. What Webb returned in its first weeks was not a polite confirmation. In July of 2022, shortly after science operations began, astronomer Erica Nelson at the University of Colorado was combing early images for new galaxies. She and astronomer Ivo Lape at Swinburne University noticed a population of strange sources. Nelson called them UFOs. ultra-red flattened objects. They were invisible or nearly invisible in optical light and screamed in the infrared. On the sky, they looked like flattened red disks, flying saucer silhouettes in the data products. Labbe took one of those little red points and ran the analysis software. Two numbers came back that should not have lived in the same sentence: a distance around 13.1 billion light-years, and a stellar mass around 100 billion suns. The universe at that look-back was only about 700 million years old, roughly 5% of its present age. System with the Milky Way's worth of stars in that shorter time is what made Labbe say he almost spit out his coffee. In reporting later, the line landed as, "We just discovered the impossible. Here there was one. There were more. In a single day of hunting, Labbe found about 6. The objects became famous under another nickname, Little Red Dots. Compact, extremely red, apparently heavy. The popular analogy that stuck was finding a fully grown adult who weighed as much as a heavy person while standing only centimeters tall. Too much mass crushed into too little size and too little time. For Lambda CDM's hierarchical script, that combination was the insult. Why did theorists call it impossible rather than merely surprising? Because converting primordial gas into stars is not 100% efficient. Feedback from young stars and supernovas blows gas out. Radiation heats cloud. Black holes, once they grow, can dump energy into their surroundings. Simulations and local calibrations both say you cannot turn every available baryon into stars on a whim. To grow 100 billion solar masses of stars by 700 million years after the Big Bang, you need either more raw material than the early universe seemed to offer in that volume, or conversion efficiencies that physics normally forbids, or a misunderstanding of what the light is telling you about mass. Headlines did what headlines do. Some asked whether the Big Bang was wrong. Some asked whether the universe was older than we thought. Some declared cosmology broken. Inside the field, the cooler response was, check the redshifts with spectra, check dust, check whether light is stars or something else, check selection effects, and do not throw out a model that still explains the cosmic microwave background, Big Bang nuclear synthesis, and large-scale structure on the strength of photometric guesses alone. Till even the cool voices admitted the early Webb samples were a problem worth losing sleep over. Spectrum matter because photometric redshifts, distances estimated from colors through filters, can lie. Dusty galaxy at lower redshift can mimic an ultra-red high redshift source. Follow-up spectroscopy with Webb's instruments became the courtroom. As confirmation stacked, the mystery did not politely vanish. Some masses came down, some objects were reclassified. The broad attention remained. The early universe looked more mature, more luminous, and more structured than many pre-launch forecasts. By 2026, the problem had company from other missions and from Webb's continuing haul. The European Euclid satellite, launched in 2023 to map dark matter and dark energy across huge sky areas, reported 31 new quasars in the early universe, including what teams described as the 2 most ancient then known. Quasars are the blazing cores of galaxies, where a supermassive black hole eats gas so violently that the nucleus can outshine the host. Finding them when the universe was only about 670 million years old doubles the headache. Not only stars, but monster black holes and organized feeding already in place. Daming Yang at Leiden University called Euclid a game-changer for this hunt, able to sweep vast areas and catch fainter primordial quasars than the old needle in a high-stack campaigns. Reports said Euclid more than doubled the known sample from that epoch in about a year, after earlier efforts needed more than a decade to gather roughly 10. Whatever final catalog settle on, the qualitative point stands. The early universe is crowded with engines that hierarchical patience did not advertise. July of 2026 also brought a barred spiral with a name like a serial number, M1149BSGZ5. Webb identified it as the most distant barred spiral, then reported at redshift about 5.1, less than about 1.2 billion years after the Big Bang. The system was described with a stellar mass around 28 billion suns, a star formation rate around 145 solar masses per year, and a central bar about 14,700 light-years long. Bars and orderly spiral arms are not the default face of a chaotic gas storm. They suggest a disk that has cooled and settled enough for orbits to organize. Seeing that architecture so early compresses the timeline for galactic adulthood. Again, May of 2026 added another insult to the slow build script. XMMVD 12075, a massive galaxy with several times the Milky Way's stellar mass that had already quit forming stars and was not rotating the way spiral disks do. Galaxies usually inherit angular momentum from the gas that falls in. Over cosmic time, mergers can scramble rotation and help build slow, pressure-supported ellipticals, finding a massive quenched, non-rotating system when the universe was under about 2 billion years old suggests transformation pathways that used to be filed under later epochs. Ben Forrest at the University of California, Davis noted excess light to one side, hinting at an interacting companion rearranging the dynamics, a merger mid-crime scene rather than a quiet old age. Layered under all of this is a second crisis that does not come from Webb alone: the Hubble tension. The Hubble constant measures how fast space expands today, infrared from the early universe, using the cosmic microwave background under lambda CDM, and you get a value near 67 kilometers per second per megaparsec. Measure it locally with distance ladders and supernovas, and you get a value near 73. That is roughly a 10% gap, with statistical significance often quoted above 5 standard deviations. The kind of disagreement that makes cosmologists sweat. In April of 2026, work associated with Adam Rees, Stefano Casatano, and collaborators was reported as unifying local Hubble constant measurements at about 1% precision. Sharper local numbers did not make the tension go away. They made the mismatch harder to blame on sloppy nearby data. Rees's line in coverage emphasized that confirming the tension raises the stakes for re-examining the cosmological model's foundations and hunting new physics that could change cosmic evolution. Stephen Finkelstein had earlier stressed that you need overwhelming evidence to discard the standard model of cosmology. The tension does not automatically equal discard, but it refuses to be ignored. Here is the link to impossible galaxy. If the local expansion rate is truly higher than the early universe inference implies, simple readings can push the universe's age downward compared with the older concordance picture. Younger universe means even less time for the monsters. Webb is weighing. The same calendar squeeze that hurts hierarchical patience also tightens the screws on every early quasar and early quenched giant. Webb's surprises and the Hubble tension are not the same puzzle, but they rhyme. Both ask whether lambda CDM is missing a chapter in how the universe evolves. So did Webb break cosmology? The field's working answer, through 2024 and beyond, has been more surgical than apocalyptic. In August of 2024, NASA and the CEEZ's team highlighted a partial fix for the impossible masses. Catherine Chwarovsky and collaborators showed that many early red sources host active black holes. Gas swirling in an accretion disk heats and shine. That non-stellar light inflates the brightness astronomers were converting into stellar mass. If you mistake quasar glare for starlight, you invent a fatter galaxy than the stars alone can justify. Finkelstein's summary after that work was blunt. There is no crisis that forces you to throw out the standard cosmological model. You need overwhelming evidence for that. And this was not it. But he and the teams also left a residual problem on the table. Even after accounting for black hole light, early massive galaxies still appeared roughly twice as common as many lambda CDM-based expectations. Weiss is not infinity. Weiss is also not nothing. The model survived. The galaxy formation recipes inside it took damage. To understand why this correction mattered, follow how astronomers weigh something they cannot place on a scale. They collect a galaxy's light through several filters and build a spectrum of energy across wavelength. Then they compare that shape with synthetic populations of stars of different ages, metallicities, dust contents, and star formation histories. A model that reproduces the colors returns an estimated stellar mass, but the answer is only as reliable as the assumptions inside the model. Add light from an active black hole and the galaxy looks heavier. Change the dust law and its age changes. Change the stellar population and the same brightness can require less mass. Webb did not simply photograph 100 billion stars, it measured light. And astronomers inferred the stars through a chain of assumption. That chain explains why spectroscopy became so important. Photometric candidate can appear distant because one set of filters sees it while bluer filters do not. Astronomers call this a dropout. At extreme redshift, absorption by neutral hydrogen cuts away light below a characteristic wavelength, producing a sharp break, but dust and older stars at lower redshift can imitate parts of that color pattern. Spectroscopy spreads the light into a detailed fingerprint. Emission lines and absorption breaks reveal whether the source truly belongs near cosmic dawn or is a red imposter much closer to us. Arc-confirmed redshift removes one escape route from the mystery. Arc-rejected candidate reminds us why the first headlines were never the final verdict. Eve and a secure distance does not settle the source of the light. Little red dots are compact enough that Webb often cannot cleanly separate a central black hole from the stars surrounding it. Broad emission lines can expose gas moving at thousands of kilometers per second around an active nucleus. Rays can reveal violent accretion, although some of these sources are unexpectedly faint in X-rays. Their spectra can look partly stellar and partly quasar-like. That ambiguity is not an inconvenience beside the story. It is the story. The objects sit exactly where two fast growth problems overlap. Galaxies building stars too quickly and black holes gaining mass too quickly. The black hole problem has its own clock. Newly formed black hole cannot become supermassive instantly if it feeds near the Eddington limit, the point where outward radiation pressure begins fighting the inward flow. Its mass grows exponentially, but each doubling still costs time. Start with the remnant of an ordinary massive star and reaching hundreds of millions or billions of solar masses by 600 or 700 million years after the Big Bang requires an almost uninterrupted feast. Real feeding is messy. Supernovae disturb gas. Radiation from the growing hole pushes fuel away. Mergers can help, but mergers also take time. Ancient quasars therefore demand either heavy initial seeds, unusually efficient feeding, long periods above the ordinary limit, or some combination of all three. Heavy seeds could come from the direct collapse of enormous primordial gas clouds, rather than from dead stars. In that picture, a cloud avoids fragmenting into many ordinary stars and collapses toward a black hole, already thousands or tens of thousands of times the sun's mass, starting heavier, buys precious doubling. But direct collapse needs special conditions: intense radiation to suppress molecular cooling, low metal abundance, and a supply of gas that remains coherent. Those conditions may exist, but how often? Euclid's growing quasar census turns that frequency into a measurable question. Few ancient quasars can be rare miracles. Dozens begin to test whether the seed factories were more common than simulations assumed. This is why Webb's galaxies and Euclid's quasars cannot be reduced to one mistaken mass estimate. Active nuclei may explain why some little red dots looked overloaded with stars. Yet the same nuclei create another puzzle. Who built the black holes so early? Solve the stellar mass crisis with accretion light, and you may move part of the crisis into black hole formation. The mystery does not disappear. It changes address. Now return to the barred spiral. A galactic bar is not paint on a disk. It is a large-scale pattern in stellar orbits, a structure that can funnel gas inward, redistribute angular momentum, and reshape star formation. Bars in the nearby universe are associated with disks that have had time to become dynamically organized. Young, violently turbulent disk can resist that organization. So when Webb sees a strong central bar at high redshift, astronomers must ask how quickly a disk can become cold enough, massive enough, and stable enough to build one. Maybe bars form faster under early conditions than local experience suggested. That answer preserves cosmology by rewriting galactic adolescence. Spiral structure carries a similar lesson. Spiral image does not necessarily mean a galaxy is calm by modern standards. Gas-rich early disks can be turbulent while still supporting ordered rotation and spiral features. lensing can magnify distant systems and reveal structures Webb would otherwise blur. Image reconstruction can also mislead if the lens model is wrong. Researchers therefore test morphology against kinematics, dust maps, and multiple images produced by the lens. Mature looking is a claim that must survive more than a beautiful photograph. When it does survive, the early timeline becomes tighter. The non-rotating quenched giant asks the opposite question. Instead of how order appeared so fast, it asks how rotation disappeared so fast. Gas falling into a dark matter halo carries angular momentum. Stars born in a disk inherit that motion. To erase the disk's coherent spin, a galaxy needs violent encounters, repeated mergers from different directions, or internal processes that convert ordered motion into random stellar speeds. Then it must stop forming new rotating stars from fresh gas. Finding both transformations completed early means the system compressed a long sequence: growth, collision, starburst, gas removal, quenching, and dynamical scrambling into less than 2 billion years. Quenching itself leaves clues. A galaxy can stop forming stars because it consumes its cold gas, ejects the gas, heats the surrounding supply, or enters a halo where infalling material can no longer cool efficiently. Supernovae can dominate in smaller systems. Active black holes can dominate in massive ones. Mergers can trigger both a starburst and the black hole feeding that ends it. The dusty star-forming phase, reported as the likely ancestor of many massive quiescent galaxies, fits that sequence. First, the galaxy burns brighter than expected, then the same event that made it bright helps turn it dark. That sequence gives Webb a cruel selection problem. Short starburst is easy to see because massive stars flood the ultraviolet. Quenched descendant can be hard to find because it no longer produces those stars and may be wrapped in dust. Surveys can overcount the bright phase and undercount the quiet aftermath. Correcting the population requires measuring how long each phase lasts. Burst that shines for a small fraction of a galaxy's life can dominate a flux-limited sample. The telescope may be showing us not the average early galaxy, but the rare moments when ordinary systems scream. The initial mass function creates a second selection effect. Massive stars are astonishingly bright and astonishingly short-lived. If early clouds made a larger fraction of them, a young galaxy would produce more ultraviolet light per unit of total stellar mass. Standard templates trained on the nearby universe would interpret that light as too many stars, but a top-heavy population leaves fingerprints. Unusual supernova rates, rapid metal enrichment, stronger ionizing radiation, and distinctive spectral features. Webb can test the idea rather than merely use it as an excuse. The question is no longer whether a different IMF can rescue the masses, it is whether the spectra demand one. Metal enrichment is especially revealing because the first stars began with almost no elements heavier than helium. Carbon, oxygen, nitrogen, and iron had to be forged inside stars and dispersed by stellar deaths. When Webb finds chemically enriched gas very early, the clock gains another hidden step. Prior generation had to form, live, explode, and mix its products before the light we observe was emitted. High stellar mass is not the only sign of maturity. Chemical history can expose a galaxy that has already lived through several cycles. While the universe itself is still young, dust tightens the same clock. Dust absorbs ultraviolet light and re-radiates energy in the infrared. Much cosmic dust is built from heavy elements made by stars, then released by supernovae or aging stars. Finding substantial dust at high redshift means enrichment and grain production happened quickly. Dust also hides star formation and reddens galaxies, complicating every estimate. It can make a closer object imitate a distant one, conceal a violent starburst, or force astronomers to revise the total energy budget upward. Dust is both evidence of early maturity and a mask over how that maturity was achieved. Reionization adds a larger consequence. The early universe began filled with neutral hydrogen that absorbed ultraviolet light. The first stars, galaxies, and perhaps active black holes produced enough energetic photons to ionize most of that hydrogen. If Webb is finding more bright galaxies at cosmic dawn than expected, those galaxies may help explain how reionization finished. The impossible abundance can become the missing photon supply. Problem in one chapter may solve a problem in another. But that only works if the galaxies leak enough ionizing radiation into intergalactic space, rather than trapping it in gas and dust. This is how scientific tension becomes useful. The old model predicts too few bright sources. Webb finds more. Astronomers adjust burstiness, the IMF dust, and black hole contamination. Those adjustments change the predicted ionizing output. Then, observations of reionization test the adjustments. Rescue that fixes galaxy counts but ionizes the universe too early or too late is not a rescue. The cosmos forces every explanation to balance more than one ledger. The dark matter halos provide another ledger. The CDM predicts how many halos of a given mass should exist at each epoch. Baryons cannot build a galaxy heavier than the available matter inside its halo. If an inferred stellar mass approaches or exceeds the halo's entire expected supply of ordinary matter, the estimate becomes physically suspicious. That was the sharpest version of the early impossible galaxy claim. Not merely fast growth, but stellar conversion efficiencies approaching everything the halo possessed. Lower the stellar masses with active nuclei or a different IMF, and the galaxies move back below the baryon ceiling. The question then becomes how close real galaxies can operate to that ceiling during cosmic dawn. Local galaxies convert only a modest fraction of their halo's baryons into stars. Feedback prevents perfect efficiency. Early systems might briefly do better because dense gas cools rapidly and accretion streams deliver fuel directly. At the same dense star formation creates intense feedback. Massive stars explode quickly. Radiation pressure pushes outward. Black holes switch on. The engine of rapid growth builds its own brakes. Simulations must reproduce that competition, not simply turn the efficiency knob until the observations fit. Bursty formation naturally emerges from those breaks. Gas collapses. Stars ignite. Feedback expels or heats the gas. Star formation crashes. Gravity pulls material back. Another burst begins. The cycle creates enormous variations in luminosity. Even when the long-term mass growth remains moderate, Webb surveys are more likely to detect a galaxy during the bright crest than during the dark trough. That bias can boost the observed number of luminous objects without requiring the same boost in underlying halo abundance. It is a statistical answer born from physical breathing, but burstiness cannot explain a genuinely old stellar population by itself. If spectra show strong features from stars that have already aged for hundreds of millions of years, then the galaxy must have started forming them even earlier. Pat pushes the first episode toward the very beginning of cosmic dawn. Age estimates are difficult because dust, metallicity, and star formation history can imitate one another. Better spectra narrow the choices. The oldest-looking systems are therefore among Webb's most important targets. They ask not how bright a burst became, but how early the entire history began. The Hubble tension must be handled with equal care. Higher present expansion rate does not automatically let astronomers subtract a simple number from every galaxy's age and declare the crisis worse. Cosmic ages depend on the full expansion history, not only today's rate. Any new physics proposed to reconcile early and local measurements changes that history in a specific way. Some solutions alter the sound horizon before recombination. Some add a brief episode of early dark energy. ARC changes distances, inferred masses, and available growth time differently. The rhyme between the tensions is real. The exact marriage remains model-dependent. Early dark energy is one proposed bridge. Temporary energy component before recombination could shrink the scale used to infer the Hubble constant from the cosmic microwave background, allowing a larger present rate. But adding that component affects structure growth and other observables. It might help one tension while worsening another. This is the pattern every exotic solution faces. The universe does not let theorists patch one equation in isolation. Galaxy counts, microwave background peaks, gravitational lensing, supernova distances, and clustering all vote. Primordial black holes are another idea sometimes invited into the room. Black holes formed in the early universe could contribute to dark matter, seed galaxy growth, or provide massive starting points for quasars. But their allowed abundance is constrained by microlensing, background radiation, gravitational waves, and dynamic. They cannot be sprinkled freely. Wherever a theory needs help, useful hypothesis must survive those limits and still produce the early structures Webb sees. Possibility is not permission to ignore the rest of astronomy. The strongest near-term tests are less theatrical. Count galaxies over larger areas, so rare bright objects, stop dominating tiny fields, measure spectra deeply enough to separate stars from accreting black holes. Map clustering to infer host halo masses. Compare morphologies with gas motions rather than trusting appearance alone. Measure stellar ages and chemical abundances. Search for the faint majority beneath the spectacular outliers. Webb supplies depth, Euclid supplies area. Other observatories supply complementary wavelength. The mystery becomes soluble when the same objects are weighed by independent methods. Gravitational lensing helps Webb reach even fainter systems. A foreground cluster bends and magnifies light from galaxies behind it, acting like a natural telescope. The magnification reveals sources too dim for Webb alone, but it also introduces uncertainty because astronomers must reconstruct the lens's mass distribution. Wrong magnification produces a wrong intrinsic brightness and size. Lensed discoveries are therefore both gifts and equations that need checking. The most convincing early structures are the ones that remain strange across reasonable lens models. Cosmic variance is another quiet danger. Webb's deepest fields cover tiny patches of sky. One patch can land on an unusually dense region and make massive galaxies look more common than they are globally. Another can land in a void. Large area surveys test whether the first fields were representative. This is why Euclid matters. Even when it cannot see every object with Webb's detail, depth finds the impossible candidate. Width tells you whether it is a freak or a population. As the surveyed volume grows, the word impossible should become harder to use. An object can be unlikely under a model without violating physics. In a sufficiently vast volume, rare objects are expected. The true crisis comes when the abundance, not the existence, exceeds predictions after selection effects and measurement errors are included. Giant early galaxy starts a headline. Statistically robust population starts a revision. That revision may be modest, stronger bursts, faster cooling, different feedback, more active nuclei. It may become deeper if the counts remain high after every astrophysical correction. Then theorists may revisit dark matter behavior, initial fluctuations, or the expansion history. The order matters. First audit the telescope and the mass estimates, then audit the galaxy recipes. Only then audit cosmology's foundation. That is not conservatism protecting an old model from facts. It is how science avoids replacing a tested framework with a more exciting mistake. Lambda CDM earned that caution by explaining an enormous range of observations with a small set of ingredients. It matches the broad pattern of the cosmic microwave background, the growth of large-scale structure, and the abundance of light elements when paired with the hot Big Bang. Serious replacement must do all of that. And also explain Webb. Saying the model is broken is easy. Building something that works better everywhere is the difficult part. No headline can skip. At the same time, success on large scales does not guarantee perfect galaxy physics. Lambda CDM specifies the gravitational scaffold more cleanly than it specifies how gas behaves inside every halo. Star formation occurs across scales. Simulations cannot fully resolve from first principles. Researchers use subgrid recipes for stellar feedback and black hole feedback, calibrated against observation. Webb has moved the calibration target into an era nobody had seen clearly. Recipes that worked nearby can fail at cosmic dawn without the dark matter scaffold collapsing. That distinction turns the mystery from a verdict into an investigation. Did dark halos assemble too early? Or did gas use them more efficiently? Did galaxies contain too many stars? Or did unusual stars make too much light? Did mature shapes require more time? Or did gas-rich disks organize rapidly under conditions absent today? Did quasar engines demand exotic seeds? Or can dense inflows sustain faster growth? Our question has an observation attached. That is why this is science, rather than a collection of excuses. The barred spiral can be tested with resolved spectroscopy. If stars and gas show ordered rotation around the disk, The morphology reflects real dynamics. If the apparent bar is a merger feature or a lensing artifact, the velocity field will betray it. The quenched non-rotator can be tested through stellar absorption lines that reveal random motions. The little red dots can be tested through broad lines, variability, and infrared to X-ray ratio. The quasars can be tested through their black hole masses and host environments. Every impossible claim comes with a way to make it less rhetorical. Variability may be especially useful for compact red sources. Stars in a galaxy do not make the entire system brighten and fade quickly together. Small accretion disk around a black hole can monitor a little red dot over time, and coordinated changes point toward an active nucleus. No variability and the stellar interpretation gains ground, although obscuration and cadence complicate the verdict. Time becomes another instrument layered on top of color and spectra. Black hole masses bring their own assumption. Astronomers often infer them from the width of broad emission lines and the luminosity of the active nucleus, using relations calibrated at lower redshift. If early quasars have different geometry or accretion states, those relations may shift. Again, the universe attacks the translator. Webb does not merely reveal unknown objects, it forces astronomers to ask whether tools built in the modern universe remain honest in the dawn. The same question applies to the IMF, dust law, and star formation histories. Nearly every inference at high redshift imports some local calibration. Webb's greatest conceptual discovery may be that the first galaxies were not simply younger versions of nearby galaxies. They lived in denser halos, accreted gas faster, contained fewer heavy elements at first, and interacted more frequently. Treating them as scaled-down modern systems was the hidden assumption behind many surprises. Remove that assumption and the universe becomes less impossible, but more alien. Alien does not mean unknowable. Physical laws still connect gas density to cooling, gravity to collapse, radiation to feedback, and angular momentum to disks. The initial conditions differ, the rates differ, the balance among processes differ. Webb is teaching astronomers which terms dominate when the universe is young. That is a deeper outcome than simply finding an older record holder every few months. Record holders still matter because each one pushes the boundary. Higher redshift galaxy shortens the available time. Heavier confirmed stellar mass raises the required efficiency. An older stellar population moves the first formation episode backward. Calmer disk challenges turbulence. Dead galaxy challenges gas supply. Quasar challenges seed growth. The important question is not which object has the biggest number, it is which physical bottleneck that number attacks. For the original little red dots, the bottleneck shifted as evidence improved. The first shock was too much stellar mass. Active black holes reduced some masses, then the shock became too many rapidly growing black holes. Other dots still showed signatures difficult to explain with a simple, unobscured quasar. The class itself may contain multiple kinds of object hiding under one red appearance. Classification is still moving because nature did not sign a contract to make every red dot the same thing. This is common when a new telescope opens unexplored parameter space. Early categories are visual and provisional. Later spectra split them into physical families. Hubble once turned faint smudges into populations with histories. Webb is doing the same with red compact sources. Today's impossible galaxy may become tomorrow's obscured quasar, extreme starburst, compact quiescent galaxy, or something not cleanly fitting any of those bins. The discovery remains valuable even when the nickname changes. By 2026, the honest picture is therefore neither cosmology shattered nor mystery solved. It is a layered revision. Some of Webb's first monsters lost weight, some remained unexpectedly massive. Brightness can be boosted by bursts and unusual stellar populations. Bars and quenched systems say dynamical evolution ran quickly. Euclid's quasars say black hole growth ran quickly. The Hubble tension says the expansion model carries an independent, unresolved mismatch. Every repair lowers one alarm and exposes another measurement to make. That is exactly how a mature scientific crisis should look. Not one dramatic observation defeating a century of theory, but many precise observations narrowing the places old assumptions can hide. First, the data challenge the forecast, then systematics are attacked, then models adapt. If the anomaly survives, the foundations move. Webb has completed the first step spectacularly and is driving the second and third. Whether it reaches the fourth remains an open question. The next generation of results will be less visually famous and more decisive. Better luminosity function, better stellar mass functions, better quasar demographic, better age estimates, better simulations that resolve turbulent molecular clouds while embedding them in cosmological volume, better cross-calibration among Webb, Euclid, ground-based observatories, and future missions. The impossible will be decided by distributions and error bars, not by one beautiful red dot, and yet one beautiful red dot was enough to change the conversation. That is the strange power of Webb. It took a theoretical timeline and placed a bright object where the timeline looked almost empty. It made the disagreement visible before the statistics were mature. Then it kept observing until the disagreement developed structure. Active nuclei, bursty stars, early bars, dead giants, and quasar seeds. The first image opened the mystery. The population is what will answer it. If some systems really are heavy, how did they grow so fast? Nilliba is the initial mass function, the EMF, the statistical rule for how many massive stars versus low-mass stars are born together. The IMF used in mass estimates was largely calibrated in the nearby, quieter universe. The cosmic dawn was denser, hotter, and more turbulent. High-resolution simulations reported in 2026 argued that the first stars formed in environments shredded by supersonic turbulence, with gas flows reaching about 4.2 times the speed of sound, fragmenting clouds into multiple pieces. That kind of birthward can change the mix of stellar masses. If the early IMF was top-heavy, richer in giant luminous stars, then a galaxy can look extremely bright without containing as much total stellar mass as a local calibration would infer. Brightness is dominated by the rare hot stars. Mass is dominated by the faint majority. If that majority exists, change the ratio and your master-like translator lies. Strayer-style studies and related work have pushed indications of top-heavy IMFs in highly star-forming systems. That does not erase every heavy candidate, but it attacks the pipeline from light to mass at the root. Second lever is bursty star formation. In the modern Milky Way, star formation is relatively steady on long averages. At cosmic dawn, simulations from the FIRE project and work led by Claude-André Faucher-Giguère at Northwestern argued that galaxies flicker. Supernova blasts eject gas. Gas cools and falls back. Fresh bursts ignite a new generation of massive stars that flood ultraviolet light. Short flash can make a modest system look like a beast to a telescope catching it mid-burst. Faucher-Giguère's point was simple. You can get enough light fast, either because the system is truly massive or because it can produce light violently on short timescales. Bursts by the second option. Then come the massive quiescents, giants that already shut down star formation. June 2026 study associated with the University of Sao Paulo reported that about 86 to 96% of those early massive quiescent galaxies first passed through a dusty star-forming phase. Lartes Sodre Jr. described the merger-driven engine. Collisions dump cold gas into the nucleus, spark a dusty starburst, and feed the central black hole. The burst consumes cold gas. Energy from the active nucleus heats the surrounding halo gas so it cannot cool and rain back in. The raw material valve closes. Star formation dies in under about 1 billion years. That pathway turns early chaos into early fossils. Explaining how Webb can see dead giants before the universe looks old enough for quiet retirement, put the explanations in one line. Some impossible masses were never that massive. Black holes fooled the photometry. Some extreme brightness is a top-heavy IMF, or a burst caught in the act. Some early quenched monsters are merger aftermaths that burned through their gas and locked the halo. Hierarchical dark matter scaffolding can survive while baryonic physics, how gas turns into stars, and how black holes yell, gets rewritten for the dawn era. What remains strange after those repaired, the residual factor of roughly 2 in massive early galaxies, the barred spiral that looks too calm too soon, the non-rotating quenched giant under 2 billion years. The primordial quasar counts climbing fast with Euclid, the Hubble tension still standing after sharper local measurements. One of these automatically deletes lambda CDM. Together they say the early universe was not a quiet nursery of faint blobs. It was a construction site running hot, bright, messy, and ahead of schedule in ways pre-Webb intuition underestimated. Hubble showed us deep fields that already hinted at surprising activity. Webb's infrared eyes and collecting area turned hints into a flood. Euclid's wide surveys turned rare quasars into a population. The scientific method here is not a single press conference. It is photometry, then spectroscopy, then population statistics, then simulations with new feedback knobs, then another round of observation. That loop is why the coffee spit moment of 2022 became the multi-year crisis and repair story of the mid-2020s. Notice what did not happen. The cosmic microwave background did not vanish. Big Bang nuclear synthesis did not suddenly fail. The broad expansion history did not become free jazz. The fight is concentrated in astrophysics inside the cosmological frame. How efficiently baryons cool, clump, ignite, and get expelled in the first billion years. Breaking galaxy formation recipes is not identical to breaking the Big Bang. Revealing a stranger dawn story can still leave the hot Big Bang standing while rewriting textbooks on how galaxies grow. Dark matter remains central either way. Hierarchical assembly is a dark matter story first. Gas follows the wells. If galaxies appear early, either the wells grew faster, or gas converted faster, or light lied about mass, or some mix. Speculative ideas. Warmer or interacting dark matter, early dark energy tied to the Hubble tension, primordial black holes as a dark component, circulators research programs, not as settled replacements. No single exotic fix is proven. The data demand better baryonic physics at minimum, and possibly new cosmological ingredients if tensions keep hardening. Webb's instruments make the demand practical. Near-infrared camera imaging finds candidates. Near-infrared spectrographs pin redshifts and emission lines. Mid-infrared instruments probe dust and heated gas. Together they separate stars from active nuclei, measure star formation rates, and catch absorption features that betray mature stellar population. When a galaxy shows signs of an older stellar crowd at huge redshift, the clock pressure returns. Stars need time to live and die before a mature spectrum appears. Time is the currency hierarchical models spend freely. Webb keeps sending invoices. Euclid adds area. Webb adds depth and detail. Ground-based spectroscopy and other facilities still matter for confirmation. The division of labor is why 2026 could deliver quasars, bars, and dead giants in the same news cycle without one telescope doing every job. Multi-mission pressure is harder for a fluke to survive. Flukes hate repetition across instruments. One decisive test will compare the galaxy's light with the mass of the halos around them. Galaxy clustering reveals how strongly a population traces the underlying cosmic web. Stronger clustering usually points to rarer, heavier halos. If little red dots occupy modest halos while appearing to contain enormous stellar masses, the stellar estimates are probably inflated. If they occupy the rare massive halos expected for true giants, the rapid growth problem survives. Clustering turns a red point into an address inside the dark matter map. Another test will follow the gas. Spectral lines can reveal how fast gas moves, whether it rotates, whether it flows outward, and whether a central black hole is driving the motion. Broad outflows expose feedback powerful enough to shut down star formation. Narrow rotating patterns support settled disks. Chaotic velocities support mergers. The same source that looks like one unresolved red dot in an image can become a map of inflow, rotation, and escape when enough spectral resolution arrives. Motion tells the history light alone can hide. The earliest galaxies also leave a background glow too faint to assign to individual sources. Add together every unresolved star and black hole from cosmic dawn, and they contribute to the diffuse infrared and X-ray background models that create vast numbers of top-heavy stars or rapidly feeding black holes. Must not overproduce those background. This is another external ledger. An explanation cannot hide unlimited luminosity below Webb's detection threshold. without the combined glow appearing somewhere else. Supernovae provide a future ledger as well. Top-heavy IMF predicts more massive stars and therefore more core collapse explosions for a given total stellar mass. Directly counting such events at extreme redshift is difficult, but lensing and long monitoring campaigns can make some visible. Chemical abundance patterns can preserve the same information after the explosions fade. Oxygen-rich gas, iron production, and unusual element ratios can reveal which stellar masses dominated the first generation. The dead stars testify about the IMF that created them. Black hole feedback can also be tested against the size of quenched regions and the temperature of surrounding gas. If an active nucleus ended star formation, energy had to couple to the galaxy rather than escape harmlessly as light. Webb can identify ionized outflows. Other observatories can probe cold gas and dust. A dead galaxy, with no sign that its fuel was consumed, expelled, or heated, would reopen the question. Quenching is not a label, it is a crime that should leave evidence. Every test narrows the same choice posed at the beginning. Were the first galaxies truly too massive and too mature? Or did unfamiliar conditions make them look that way? The answer will probably not be one clean side. Some objects will lose mass when black hole light is removed. Some will remain heavy. Some spiral features will be genuine disks. Others will be mergers caught at flattering angles. The universe can solve a population with several mechanisms at once. Mixed answer is less dramatic than one broken equation and more faithful to a sky filled with different histories. Return to Nelson's UFOs and Labbé's coffee. The cultural power of that moment was the collision between a clean forecast and a dirty sky. Forecasts said faint, small, messy. The sky said red, compact, luminous. Science advanced by asking which part of the pipeline failed: distance, dust, AGN light, IMF, burst timing, or the formation model itself. The honest scorecard today is mixed. Pipeline failures explained part of the panic. Formation physics still had to stretch. Cosmology's core frame bent under the Hubble tension from another direction. The universe did not become nonsense, it became harder. Harder is not a failure of the James Webb, it is the point of building it. Telescope that only confirms PowerPoint slides is a postcard. Telescope that forces theorists to rebuild the dawn is a scientific instrument. Webb found that the early cosmos could manufacture light, structure, and dead weight faster than the public story allowed. Whether you call the results impossible galaxies or underestimated galaxies depends on which explanation you weight. The nickname stuck because the first numbers felt like a violation. The follow-up work turned violation into a research agenda. So what did James Webb really discover? It discovered that the first billion years are richer in bright, compact, structured, and sometimes already quenched systems than hierarchical common sense expected. It discovered that measuring stellar mass at extreme redshift is a trap if you ignore black holes and atypical stars. It discovered, together with Euclid and the distance ladder community, that the early universe and the local universe are both talking back to lambda CDM in uncomfortable ways. It did not hand us a single slogan that cosmology is dead. It handed us a stranger opening chapter. Did it break our understanding of the universe or reveal that the cosmos has been hiding a much stranger story since the very beginning? The second reading fits better once the dust settles. With a caveat, the stranger story is still being written in papers, not carved on a monument. Lambda CDM remains the scaffold. Galaxy formation at cosmic dawn is the wing under renovation. The Hubble tension is a separate crack in the scaffold's expansion history. Webb's gift was forcing both the renovation and the crack into public view with images sharp enough to spit coffee over. The early universe was supposed to look like unfinished business. Instead, Webb keeps finding construction already several floors up, sometimes with the lights blazing, sometimes with the power already cut. That mismatch is the discovery. Everything else is the work of figuring out whether the flaws are real mass, bright illusions, or both. And every new spectrum makes that choice harder to fake. Light can exaggerate, structure can mislead, but independent measurements eventually force the hidden history into view. Thank you for watching.